Hey everybody, welcome to podcast number 11, where we're going to talk about buffers and how we make buffers by something that we call partial neutralization. Because once we understand how to make a buffer from partial neutralization, then we'll understand what happens when we add a strong acid or strong base to those buffers as well. So let's take a look at how we can make buffers by an alternate route, not by the way that we did it earlier, but this is the way that most people make an actual buffer, is by what we call partial neutralization of a weak acid by a strong base, or vice versa of that, which is my second bullet point there. So what if I had a weak acid? All right, we're going to have some weak acid that I'm going to call, right, my HB is my weak acid. What it says by partial neutralization by a strong base. Okay, so I'm going to add a strong base to this. All right, what I'm saying then is, what if I had like 1 mole of HB? All right, and I added in a strong base. Okay, what happens is that these two are going to react together, and they actually react completely, which is why I have forward arrows on this slide. And they're going to form B minus, that's the conjugate base of that acid, plus some water. All right, what if I had 1 mole of weak acid, and to that I added in, say, 0.4 moles of strong base? Okay, well, the change in this would be, all right, they're going to react 1 to 1, and so their limiting reactant is the OH. So they're going to go down each by 0.4, and the B is going to go up by 0.4. And so at equilibria, I'm going to have 0.6 moles of weak acid. I'm going to have none of the strong base, and I'm going to have 0.4 moles of weak base. So at equilibria, we have some weak acid and its conjugate base. We have both of those. We have a buffer. Right, up above, I can do the same thing with a weak base and a strong acid. And again, if I say had 0.18 moles of H plus and I added that to 0.28 moles of ammonia, and I started with none of the ammonium cation, we're going to go down by the limiting reactant, which in this case is the strong acid, and we're going to go up over here. And so at equilibria, we'll have used up this strong acid, but we're going to be left over with a little bit of the weak base, 0.1 moles of that, and we're going to have made a little bit of weak acid, 0.18 moles of that. So we have a weak acid and weak base. We have made a buffer. All right, let's work a sample problem here where we want to know which of the following would form a buffer if we added them to 650 mils of 0.4 molar strontium hydroxide. Okay, so in order for us to have a buffer, right, we must have weak acid and its conjugate base in a solution. All right, so what we're going to do is we're going to figure out, right, can we produce both a weak acid and a conjugate base? Those can be the two things that are prepared. So the first thing that I need to do is say, okay, from my 0.4 molar strontium hydroxide, right, how many moles of hydroxide are there? So let's start with the fact that I have my 0.4 moles of strontium hydroxide per liter. All right, and then we know that this is a 0.650 liter solution. And then I also know that there is going to be 2 moles of hydroxide for every 1 mole of strontium hydroxide. So for every one of these parts of the problem, right, we are going to say that there are 0.52 moles of hydroxide present. All right, what if we then added that to 1 mole of hydrofluoric acid? Would we prepare a buffer? Right, so let's first off think about what is in the problem. The reaction between our hydrogen fluoride is a weak acid with the strontium hydroxide, which is a strong base. All right, so we have a weak acid strong base problem. Let's see if this is a partial neutralization problem as well by setting up a little bit of an ice table on our next slide. All right, so if we continue on with that problem, I can set up an ice table where I have some HF plus some OH are gonna come to equilibrium with some fluorides and some water. Again, the water is a liquid, I don't care about it. And we found then that I have 1 mole of HF. We started with 0.52 moles of hydroxide. So the limiting reactant is the hydroxide. So the reactants are going to go down by that amount, and the products are going to go up by that amount. And so we're going to end up with some weak acid, 0.48 moles of weak acid, and 0.52 moles of the weak base. That is a buffer. All right, what happens if I added it to 0.3 moles of HF? So again, I've got my HF, I've got my hydroxide. So in this case, I'm only starting with 0.3 moles of HF, but I still am starting with 0.52 moles of hydroxide. Well, now the limiting reactant, the smaller of those two values, is 0.3. So they both have to go down by 0.3, and the F's going to go up by that amount. So we're going to be left with none of the HF. We're still going to have 0.22 moles of hydroxide, and we're going to have 0.3 moles of fluoride. So once we've reached our equilibrium, once this reaction has taken place, notice that I have just a strong base and a weak base. Strong base plus weak base does not equal a buffer. All right, my part C on this problem, kind of crammed down there at the very bottom, says, all right, what if we had 0.3 moles of NaF? All right, well, even just thinking about this, in this case, right, we have a weak base trying to react with hydroxide. Well, a weak base, again, plus a strong base don't equal a buffer. They cannot make a buffer. There's no way to get partial neutralization. There's no way for us to make a weak acid from those two reactants, and so there's no way for us to make a buffer. All right, next we're going to have another sample problem. As I said way earlier in these podcasts, right, there's a ton of sample problems from this chapter, because the more we see, hopefully the better we'll get at them. I want to calculate the pH of a solution where we're mixing 25 mils of pyridine with 65 mils of hydrochloric acid. They give us the Kb for pyridine. All right, so when we react our pyridine, right, and our HCl, we are going to get this overall reaction here. All right, now, first things first is I'm going to determine the number of moles of both the pyridine and my hydrochloric acid from the information given to us in our in our problem. All right, so I have pyridine, which is 25 milliliters of pyridine. And I have the density of that 0.978 grams per milliliter. Now we're going to convert that into moles by using the molar mass. So 1 mole of pyridine happens to weigh 79.1 grams. And we're going to end up with 0.309 moles of pyridine. All right, next off, right, we are going to do the same thing with our HCl. And so in this case, we have volume and molarity. And so I've got my 0.0650 liters times 2.75 moles per liter. And we end up with 0.180 moles of HCl. I could set up an ice table then and see what we have at the end. So I have 0.309, I have 0.180, and I have none of that. These are both going to go down by 0.180. This is going to go up by 0.180. And so we're going to end up with 0.129, none of that, and 0.180 there. So I've got my pyridine, which is a weak base, and I have its conjugate acid over there on the product side. I have made a buffer. All right, now can we then, from that buffer information, calculate the pH? Okay, so we are doing a buffer problem. And remember, when I work a buffer problem, I always like to do that my H plus is equal to Ka times the concentration of acid over the concentration of base, right? Or in this case, we can do the H plus is equal to Ka times the number of moles of acid divided by the number of moles of base. So we're going to use that. So we need the Ka. We have the Kb in this problem. So the Ka is equal to Kw over Kb. So 1 times 10 to the minus 14th over, and the Kb is 1.5 times 10 to the minus 9th. So we get 6.7 times 10 to the minus 6th. Now we can plug in our values here. And so our H plus is 6.7 times 10 to the minus 6 times, all right, the number of moles of acid. All right, between the two, right, the pyridine is the base. So the acid is its conjugate acid is the 0.180 moles. The pyridine was 0.129 moles. And so our H plus concentration is going to equal 9.3 times 10 to the minus 6th. And hopefully by now, we know how to calculate a pH by 2 in the negative log of that, and we're going to end up with 5.03 is going to be our pH for that problem. All right, so that ends another podcast. We're going to then turn our attention over to, all right, what happens to the pH when we add a strong acid or strong base to a buffer?